Thanks again for showing up or thanks for showing up for the second talk. And so let me just again begin by just kind of communicating, like the basics over here is just to kind of frame the way I'm going to do things. The kind of spirit is very much applied math. What we're looking for is a model that will provide us with some insight. And one of the things that we're kind of looking for in this model is kind of like theory for deep learning, but by theory over here, what I really mean is kind of places of contact with mathematics where we kind of have tools. So we're kind of looking for connections with DLN and kind of other areas of mathematics to kind of find places where we can get insight. And so I just want to begin by reminding you again about the model. So our model is that we're running training dynamics on a big space. The big space is a collection of matrices. The matrices are each D by D matrices, no symmetry assumptions or anything. So we've got D squared entries in each matrix, and we've got n such matrices. And these two parameters correspond respectively to the width and the depth of the network. The relation to deep learning is that what we're learning is a linear function. And so our linear function is represented by this matrix W without an underscore. And this matrix W without an underscore is a product of all of these matrices in the chain. And the product is written out this way because we're thinking about it as layer by layer compositions. So of course, if you're doing true deep learning, you would have parameters in here and you would be doing functional compositions. But over here, we're just doing a linear function. But nevertheless, kind of the spirit of today's talk is really to show you kind of that there's structure, and the structure has relation to true deep learning. Okay, so what we're doing is gradient dynamics. And so just to kind of remind ourselves, when we're doing gradient dynamics, we have to have a state space, an energy function, and a metric. And so the state space is what I just stated, the space of all these matrices. What's interesting is that the energy function depends only on this observable. And the metric is the standard metric on MDN, so it's a standard metric on R n d squared, so this big high-dimensional space of dimension n times d squared. And this is a computation, so it's really because this computation is really related to the change of variables formula over here, and that's how we get this gradient flow. And so this is a d by d matrix, and what it really just means is entry-wise differentiation of the energy function with respect to the ijth entry of the energy. And so our energy, to be concrete, so this is really the simplest type of energy. So the important thing over here is it's a gradient flow. Gradient flows have been studied for 100 years in mathematics. What's interesting about this gradient flow is the overparameterization structure and the degeneracy of the energy. So the energy is zero on any matrix which has elements being, diagonal elements being A1 through AN. So this is just an energy function chosen for concreteness. And to kind of like, it's each kind of like in making, so it's a modeling, it's kind of, what I really like about the work of Arora, Cohen, and Hazan over here is somehow they use their insight to find a really, really good model. And by that I mean that it's a model where there's kind of interesting mathematics, and the interesting mathematics seems to kind of give us insights into the true problem. Though of course there are many technical challenges, in joining these dots. So in the last lecture, I pointed out, a kind of very interesting dynamic structure, a very interesting geometric structure of this gradient flow. And the interesting structure of this gradient flow, so the first theorem proven by Arora, Cohen, and Hazan, was that there's a collection of invariant manifolds in the phase space. So in relation to, Andre, I didn't feel like I quite got your question last time. But what that means is that so this is just a kind of geometric sketch. Of course, it's a very high dimensional space. So what that really means is that if you start out on any point on one of these manifolds, so these conic sections, then for all time, you're going to be living on this manifold. So, perhaps a better way of drawing it is like a three-dimensional thing and you're just moving along this cone. So you're not allowed to move off it if you're solving these equations in exact arithmetic. So that was the first theorem. The second theorem was that it kind of pointed to the special rule. So there's this entire foliation of the space by these invariant manifolds. And we're going to do a little bit of dimension counting in just a second to form a better feeling for this invariant manifold. The invariant manifolds are parametrized by a collection of constants which are written out as the G underscore. And so the number of parameters that are used to kind of describe any of these manifolds is n minus 1 symmetric matrices. So you've got n minus 1 times d plus 1 over 2 parameters. So you pick one of those parameters, you get one of these curves. But out of all of those, one of the most special ones is where you set all of these guys to 0. So when you set all of those guys to 0, you get a true, like you get literally like a cone. Okay, not a cone in the sense of STP or something where you kind of got a one directionality. It's really like a cone in kind of the kind of way we learn it in, let's say, high school trigonometry or something. And so when one begins over here, this is an invariant manifold. And so when we're living over here, this is the upstairs. We've got the training dynamics in this high dimensional space. And then when we compute the observable, in principle, it's just a function of this point. But what actually happens is that you get a flow over here. And this flow is, I wrote it out over here. So that's the Riemannian submersion structure. So this was found by Bar, Rahut, Tistiger, and Vestiggenberg. So it turns out that you've got this Euclidean gradient flow over here. And when you push it down from this particular conic, so the name over here was M0. Let me just remind you, let me call it the balanced conic. I'll sometimes use the word balanced manifold because that's what Aurora Cohen and Hazan called it. It's not a manifold, so I feel like I need to be a little bit careful, though in some sense that is a more convenient terminology. So that one is special. And when you push down from that one, you actually get a Riemannian gradient flow downstairs. Okay? So what we're looking for, so going back to this point of kind of finding the spirit to get insight, what we're trying to get insight into is, of course, true deep learning, but let's kind of do it at a more basic level first, just to get insight into this dynamical system. So, one of the things you do is, of course, you do numerics on this. It's just ODE, so you kind of solve the ODE numerically, see what happens. So what you find is that despite the fact that the energy function is degenerate, typically as t goes to infinity, this guy over here is converging to a low-rank matrix. So in the 2x2 case, there's a kind of manifold of low-rank matrices. Let's say all of this is the zero energy set, but somehow you end up at kind of special locations. Okay, so that's a very, very interesting phenomenon. A second one is somehow it's certainly the case that the space is foliated by all of these guys. And it's certainly the case that we have a nice theoretical result regarding the projection down of the gradient flow for this particular conic. But in fact, it turns out that this particular conic is actually important in practice too. So when you're actually doing numerics, not solving an exact arithmetic, what you find is stuff kind of comes down to this guy. So this balanced conic is somehow attracting stuff. Okay? So to cut a long story short, the talk today is really about trying to understand this phenomena. So there are two phenomena over here. And it turns out that with both of these phenomena, we have, let's say, theorems that shed light on this. Are these theorems perfect explanations? No, we're not there. But it's kind of a good model because you keep pushing, you keep learning stuff. The stuff that you learn kind of leads you into kind of different areas of mathematics. And so last time where I kind of ended up was the statement that, when you look at this balanced conic, you somehow see this kind of structure, which was known in Riemannian geometry in minimal surfaces theory, somehow showing up again in this problem. So, as Philippe pointed out, okay, great. Like, here's this object that shows up over here. There's an object that showed up already in geometry. Like, so what? So, I think that's a phenomenon that I would like to shed some light on. And so the phenomena over here is that this conic has zero mean curvature. And there's a phenomena over here of kind of rapid decay onto this manifold. This second phenomena is clearly a numerical phenomena related to discretization. So the way I'm going to kind of try to understand that phenomena is by looking at stochastic dynamics. And so what I'm going to try to do to you is to kind of give you a feeling for the type of mathematics that's coming in. And that feeling involves kind of two separate pieces. So one of them is a kind of collection of exact formulas, which are related to just a collection of exact formulas. Let me just kind of state the formulas rather than give you the philosophy, and then try to give you a sense of kind of how noise and curvature are related. So just to give you a sense of the formula, let's just kind of understand this. Let's just do a little bit of dimension counting and just focus on that manifold, and I'll kind of make a group orbit within to kind of look at our overparameterization a little bit more carefully, and I'll give you an interesting formula. So let's just do the dimension counting. Okay, so the dimension of our full space is capital N times D squared. The dimension of, so the number of constraints in that equation. So what I'm trying to do over here is just to figure out what's the dimension of any of these manifolds, or what's the dimension of the balanced cone. So the number of constraints, well, I've got n minus 1 symmetric d by d, symmetric d matrices, so n minus 1 d times d plus 1 over 2. So the dimension of any of the mg is clearly nd squared minus that. Okay? And if you do the calculation, so let's just write this nd squared out as d squared plus n minus 1 times d squared. So this is d squared plus n minus 1 d minus 1 over 2. Okay? Okay. So that's the dimension of symmetric matrices. That's the dimension of antisymmetric matrices. And antisymmetric matrices are the Lie algebra of the orthogonal group. And that's going to come into the picture. So let me just make a picture over here, again, of kind of the Riemannian submersion. So I'm going to fix a matrix W over here. And associated with the matrix W, I'm going to look at, let me call it, is equal to W belongs to M0, or let me call it something else, because this is going to be, let's call it CW. So it's the W belongs to M0 such that Wn W1 is equal to this guy. So I'm taking a slice through this cone, and the slice is corresponding to this guy over here. Okay? So this guy has dimension is equal to d squared. So that's the dimension down here. So that's what this corresponds to. Okay? So, I'm trying to understand the dimension of the balanced cone. And so I've got d squared plus these guys. So the d squared corresponds to fixing a slice, fixing what's going on downstairs. And as for this, the dimension of CW is now going to be n minus 1 times d minus 1 over 2. And the reason you get that is it's the dimension of the orthogonal group n minus 1 times. Okay? So what's really going on over here is that imagine that you've got this equation. Sorry? Same thing. Because I take antisymmetric matrices, I take the exponential, and I get the, let's say W, let's call it WP plus 1, WP, W1. So if you've got a matrix of this sort, observe that if you take, so think about like an element over here would be, let's think about it as it's a collection of matrices. So each of these matrices is an orthogonal matrix. And so let's go over there and take one of those matrices and do QP plus 1 transpose, or let's call it QP transpose QP. Okay, because this guy is just the identity. So overparametrization comes with a natural, invariant structure, and over here we can really characterize the invariant structure. It's corresponding to a group action. So this guy has a group orbit, and one of the kind of nice features of the DLN is you get a collection of exact formulas. And so let me state a theorem It's basically a calculation, but you kind of have to know a little bit of machinery to get this calculation. It's a lovely calculation by my student Tianmin Yu. So theorem. Okay, so I'll kind of come back to this theorem at the end of the talk. I want to give you kind of two flavors. So one flavor is kind of the low rank stuff. So this is kind of related to these exact formulas. And then there's the exact decay and mean curvature fact, which will be kind of coming from a different heuristic. But over here, the theorem is that the volume, so like the n minus 1 times d minus 1 over 2 Lebesgue volume of CW is equal to, let me just get that right. So there's a universal constant, and then it's the product 1 to the 1/2, where lambda 1 are the singular values. W. It's a theorem, this is by. Okay? Yeah, absolutely, absolutely. So, one of the consequences of the balance condition is that the singular values are the same, but the balance condition is saying more than the singular values. So actually, that took us a little bit. Exactly. So there's a very nice parameterization, so the singular values are the same. So what I'm really just saying over here is that there's an exact formula for the volume of a group orbit. So the statement over here is that we can understand, so what we're saying, so we had a kind of foliation of the full space by the kind of G's. Now we're just focusing on this cone, and this guy has a separate foliation, which is corresponding to a group action. And it's a kind of solvable group action in the sense that you can just sit down and you can compute stuff. Okay, so it's a kind of non-trivial calculation, but it's like a 3-page calculation, a 2-3-page calculation, but it's a nice formula.
So this is just capturing the fact that the only, because the left singular vectors of W1 and the right singular vectors, the only freedom that is left is one of them.
That's right. That's exactly it. That's exactly it. Right. So in fact, yeah. So as I was saying last time, there are kind of several parameterizations of the balanced cone. And this goes back to something that John said, like, so, you have a very clean equation, or I've wiped out the equation for the definition of the balanced cone. You can use that equation in different ways, but we still don't have an absolutely clear-cut conceptual understanding of the balanced cone. Okay, but one of the things that's going to come out, so today's talk, actually, the area of contact I'm going to be making with is random matrix theory. And so kind of like, this is kind of random matrix theory type stuff. You get kind of exact formulas, and exact formulas for actually the concept that I'm looking for over here is entropy. And entropy quantifies degeneracy. And what I'm really saying is that the entropy of, that I'm going to associate a natural entropy to the point down here. And the entropy is going to be the logarithm of the volume of the group orbit. Okay, so I've got the group orbit. I've got an exact formula for it. And so a quantity that I can define associated to this is a sort of Boltzmann entropy, which is the logarithm of the volume of the group orbit. Okay. So for now, I will stop with this formula, and now I'll kind of try to give you a feeling for the curvature effects. And the empirical phenomena that I'm trying to understand now is this one. So this formula and a collection of formulas of this sort, so like Jules Ferrastro, Nadav Cohen, and I were able to find kind of formulas for the volume form of the metric, and those look very much like RMT type formulas. And so this is a kind of example of that vein. And what happens with these formulas is you can kind of see that these formulas will kind of blow up in particular ways, as for example, the singular values go down to 0. So the divergence of these singular values, it kind of tells you like where space is, like what are the points of max entropy and those will correspond to kind of the low-rank matrices. So low-rank matrices are singular because we've got the space downstairs, but the space downstairs is equipped with a metric which is not the standard metric, and so most of space is actually around the low-rank matrices. So that's the kind of type of kind of heuristic insight or type of phenomena that's going to show up over here. Okay, so what I really want to do is to now switch to the concept of mean curvature, and I want to do it in a way that doesn't involve any geometry. So I'm going to do it for you through examples. And the kind of, so I want to kind of show you a couple of theorems, right? Because it's kind of good to have models which give insight, and it's good to kind of have theorems which connect the DLN to kind of areas where we really understand stuff. So you can kind of see the richness of the DLN on one hand, which is basically the richness of deep learning as a mathematical theory on the other hand. And so kind of to also show you that we've got tools, but these tools come from kind of unexpected places. Okay. So for part two, I'm going to do something called mean curvature, but we're going to do it as propolis, and I'm going to get it with, I'm going to kind of show you a nice fact involving stochastic differential equations, and then we're going to kind of build from this example to get other ideas. Did you have a question, Austin? No? Okay, cool. Oh, absolutely. Yeah, you're completely correct. Absolutely. Yeah, otherwise, of course, it would be, yeah, totally. Yeah, totally. Okay. Okay, so what I'm going to do is just show you an SDE, and what we're going to do is we're going to, so the critical insight over here, so, it's really related to kind of noise in the system, but we're going to break up our noise anisotropically. So we're going to look at noise in the tangent directions and noise in the vertical directions separately. And the easiest place to see this is just a very simple calculation involving circles, concentric circles. Okay, so let's just sit in, let's say we're sitting in RD. And let me say that I've got Brownian motion in RD. Okay, and so let's say that that's the point X. What I'm going to do is I'm going to break space up into the tangent space to, so let's call this SR. So SR is equal to sphere of radius R. Okay, and I'm going to kind of, what I'm going to do is I'm going to write out an SDE of the following sort. Okay, so let's look at this matrix. So let's say P of X is the identity minus X transposed over X squared. Okay, so what this matrix does is it's giving you a projection onto the tangent space. Okay. This is the orthogonal projection onto the tangent space of the sphere with R being mod X. And I'm going to just look at this SDE, dxt is equal to projection at xt dbt. Okay, so just an etho SDE, but all I'm doing is I'm projecting my noise into the tangent direction. So it's kind of like, imagine that you're taking random steps up and down. So you're just kind of taking random steps, so you're going to kind of jiggle in the tangent direction. So is the SDE clear? Okay. So I don't know if you guys have done this calculation before, but it's a cool calculation. So, if you've got a smooth curve, so if this were not an SDE, so if B of t were some smooth function, then of course if you were to project onto the tangent direction, what you would get is you would get a flow which kind of took you along the tangent direction to this curve. But this is not something that is smooth. This is Brownian motion. And so let's compute the rate of change of the radius. So let's say RT, where RT is equal to the square root of XT transposed XT. Okay, I'm just looking, or let's write it out this way. Okay, so this is actually the core calculation. Once you understand this calculation, there's a bunch of stuff that comes after that. It's slightly harder, but in some sense, this is the key insight. Okay. Aha, let's do the calculation. We'll find out. So in fact, it's going to be absolutely clear that it does not, but I'm going to compute it. So, so the SE is well defined, and I'm just going to see what the rate of change of the radius is. And so the point really is what is the etho correction, to tell you exactly where I'm going. Okay, so we've got d xt squared, that's basically d. Okay. And so by the chain rule, you get a term of this sort. Okay, so that's the usual chain rule. But then there's an etho correction, because we're doing etho calculus, and it turns out that the etho correction in this case is that. Okay, so what's happened is that I've set up my noise in a way that it's orthogonal to xt. So this stuff is 0. That's the construction. But there's a non-trivial term. Okay? And if you compute the non-trivial term, you'll see that what you're really looking at, so you've got kind of the independent noise. So what you're really doing is really just looking at the noise in the tangent directions. And if you work this out, this is d minus 1 times dt. Okay? So what's actually happened what we've really found is I've got an SD for x, but what this is telling me is dr squared, so because that's what is d minus 1 dt, or what's the same thing, you can just rewrite this now as an OD. So that was an SD, but now we've got an OD down here. And if you work this out, so I'm just going to write it out as RT dt is equal to d minus 1 over 2 RT. Okay, so your particle is kind of always going tangentially, but actually it's drifting outwards. So it's really an SDE fact, and it's an SDE fact which tells you that despite the fact that you're kind of upstairs and moving always, so you're kind of always moving tangentially, or it seems to you always moving tangentially, pushing outwards. And so if we just look at the radii, what you actually find that if you look at these entire collection of orbits, these orbits are just moving out normally, and so the orbits move by motion by minus 1/2 curvature. Okay, so the curvature of a circle, so motion by curvature means that you've got a curve and the speed of the curve, the normal velocity of the curve is the curvature. When you've got a circle, the curvature is normalized kind of this way. So you're moving outwards, so it's minus, that's where the minus factor comes from. And the 1/2 is just because of this chain rule over here. So it's a super simple calculation in etho calculus. Okay, so if you haven't kind of seen etho calculus before, you really just need to understand what the etho chain rule is, or the etho formula is. But just trust me, it's like about as simple a calculation. In etho, the real point is the geometric interpretation of what's going on. So tangential noise actually gives rise to curvature. Okay? So this is an observation that we've used actually in all sorts of different ways. And so let me give you a fancier version of this theorem. And in some sense, it's this insight which we believe is responsible for the kind of structure or for the stability of of the balanced cone. So it's kind of, this is actually a general fact. But again, let me explain this general fact to you through examples. But let me actually pause because I feel like I don't want to go too fast. This is in some sense the critical insight of today's lecture. It's really the role of curvature, but it's the interplay between curvature and tangential fluctuations. So tangential stochastic fluctuations will give rise to a deterministic normal evolution by curvature. So that's the fact you need to remember. Yeah. Then you would not move. Yeah. Yeah. That is exactly it. That's exactly it. But let's build up to it. Okay, but it turns out with the balanced cone, we are not quite there. So it's a little bit more subtle than that, but it's related to the geometry. But let me give you a non-trivial theorem in this vein to kind of make the connection with, I just gave you a kind of formula which I had the random matrix theory flavor. So now let me give you an insight into random matrix theory using a fancier version of this. Okay, so here's a kind of more sophisticated example. Say example from RMT is for random matrix theory. Okay, so now we're not going to be, so what we're going to do is we're going to take a big space and then we're going to foliate that big space. So over here our big space was RD. We foliated by spheres. But now we'll look at something which is we'll look at a matrix space and we'll foliate the matrix space because that's what we were doing in the DLN. Okay, so let's look at, so this will be the space of Hermitian matrices, complex Hermitian. Okay, and so the notation that I'm going to use is I'm going to take a typical matrix M and I'm going to write it out as U lambda U star. So these are the eigenvalues or diagonal matrix of eigenvalues. And that's something which is unitary, UD. Okay, so we're looking at diagonalization. And so I'm going to kind of write out again. So Riemannian submersion keeps showing up in all of these problems. And so here's how it shows up in this problem. And I'll play with this insight like slightly differently. And now this calculation is kind of, it's a little bit more sophisticated than this, but the basic insight is the same. So the picture is going to be as follows. So there's my space of Hermitian matrices. And the space of Hermitian matrices is going to be foliated by group orbits. Downstairs is going to be, let's use D. Okay, so upstairs over here is going to be a matrix. Downstairs over here is going to be its diagonal matrix. And this guy over here, I'm going to call script O lambda is equal to okay, so this is a group orbit. This is the space of Hermitian matrices. Yeah, absolutely. So I'm getting all messed up. So I was using D and I was using M. Okay. Okay, so in this case, it's not so easy to write out like exactly what the projection is, et cetera, et cetera. You get some brackets and stuff like that. But the geometric idea is absolutely clear. At any point over here, I can break the space up into a tangent direction and a normal direction. And what I'm going to do is to generalize this construct, but now I'm going to add in also an anisotropy parameter to get kind of a fancier theorem. So what we'll do is we'll fix a number and it's allowed to be infinity. And so at any M belongs to Hermitian D, set P M is equal to projection onto the tangent space. And let's say PM perp to be projection onto tangent space of M or lambda. Okay, and these inner products are computed with respect to the standard Frobenius norm on the space of Hermitian matrices. So kind of just the matrix generalization of RD. Okay. And so now finally I have to write out my SDE. And so let's write out the SDE. So let's call it star star. So the SDE I'm going to write out is DMT is equal to projection at MT. Okay, so now I need a diffusion to begin with. So let's say XT is equal to Brownian motion in the space of Hermitian matrices. Okay. So it's always like you've got your ambient noise, and when you're writing out your SDE, you're kind of writing out an SDE with respect to this noise. Okay. So the SDE that we're going to write out is DXT, is the projection DMT is the projection at MT, DXT. So I need to get my beta factors right. I don't want to write the wrong SDE out. I think I know it from the top of my head, but I just want to check. I don't want to download papers from the archive in the middle of a talk, but okay. Okay, yeah, I was making a mistake. Plus. Okay. So now I'm doing a slightly fancier one. In the case when beta is infinity, it's going to be just a projection onto the tangent space, but I'm also allowing myself a little freedom. So what I've done is I've taken the ambient noise and I've rescaled it and made it an anisotropic noise, where the anisotropy kind of has just two parameters. I want to kind of think about. So the real insight over here is what we're trying to understand is what does noise in the gauge direction, noise in the kind of null directions do? And of course, the insight from the circle is that if you've got noise in the tangent directions, then it gives you kind of a curvature effect, a mean curvature effect in the normal directions. And so now we're looking at a matrix version of it. So we've just taken the matrix space, we've foliated by a group action, just like you can think about the sphere as being obtained by quotienting by a group action, and we want to understand what happens over here. Anyone want to guess? What's the theorem, Joe? Okay. Sorry? Okay, that's true, but you want, we want actually, so over here the game is even more interesting than that. What you want is explicit formulas for the mean curvature. And in fact, you want to say that the formula for the mean curvature is that it's the gradient of the entropy. And that's actually the structure of the theorem. So this is a theorem with Dominic Inauen. So actually this was from, so Dominic Inauen and I came up with this, and then my student, Huang, also kind of came up with the version of it. So this is from, actually, that's not quite, that's my name, and that's the year. And so the theorem is that the eigenvalues, so assume, okay, you need a little bit of bells and whistles, you need like beta greater than 1 so that you don't have a blow-up time, etc. But assume MT solves star star, then lambda t solves d lambda I is equal to sigma j not equal to I, 1 over lambda I minus lambda j dt plus square root of 2 beta d, so strictly speaking, one should be a little bit more. same law as, let's call it D, W, I, where W, T, is Brownian motion in RD. Okay, so the statement, the theorem really is that, so there's a very, very famous ODE, the central SDE in random matrix theory, so this is called Dyson-Brownian motion, and what we're saying is that the curvature effects, you kind of take, curvature effects can basically give rise to Dyson-Brownian motion, and in the particular case, so here's the corollary, so when beta is equal to infinity, i.e. dmt, so I'm solving an SDE, so I'm going strictly tangentially as I was earlier. Then O lambda t evolves by motion by minus 1/2 curvature. Okay, so we were actually rather pleased with this theorem. So this is an ECP last year. So we were rather pleased with this theorem because it came out of this simple insight. But it turns out that this, the ODE over here, the SDE over here, so three special cases of this SDE for beta is equal to 1, 2, and 4 were kind of found by Dyson in the 1960s. There's a kind of separate construction of Dyson-Brownian motion by numerical linear algebra, so by Ioana Dimitriou and Alan Edelman in the year 2000. There's a kind of quasi-result by Alice Guionet and a couple of other people, so I forgot the first name. But what we have over here is a very, very simple geometric construction of the fundamental SDE in random matrix theory. And the real point, again, is just this very, very simple effect at heart, which is that noise in tangent directions gives rise to curvature effects. So the computation of the SDE over here, so kind of to go from the MT to the lambda, this is a little bit more tricky because you have to kind of do eigenvalue perturbation theory rather than just the kind of easy SDE that I showed you. But in some sense, it's actually standard stuff in RMT. What you really like, the insight is really in the kind of construction, in the choice of the SDE upstairs. So again, I kind of want to focus your attention on kind of certain basic geometric themes. So the idea of the Riemannian submersion. What's changed in today's lecture is the combination of Riemannian submersion with the kind of notion of tangential noise. Yeah. You can basically do it in the real setting. So we kind of did Hermitian setting because somehow beta is equal to 2 is special, and there's a kind of, so when beta is equal to 2, the noise is totally isotropic. So when beta is different, so somehow when you do Dyson-Brownian motion, you think about beta as a temperature parameter. Over here, we're thinking about beta as a kind of anisotropy parameter. And I can make a similar calculation. So I can make a similar calculation for symmetric matrices, but the beta dependence will be slightly different. So to kind of get things exactly right, you do want to do it with Hermitian matrices. But you're exactly right. You can get it out a different way. Yeah. No, so it's one of these things where it's really weird. So we sent it to communication maths physics and got rejected. So all my best papers get rejected from communication maths physics. It's like a general pattern in my life. But of course, because there's so much is known about Dyson-Brownian motion, you're like, what can you do? Like, what's the point? So it's like, it's acute observation, and so what? But for us, actually, the observation came out of this big theory. And so we are like, actually, once you get this observation, you can do a lot with this observation because you can take this observation to all sorts of different directions. The surprise in some sense is that you can compute the mean curvature exactly, and the exact calculation of the mean curvature turns out to being the Coulombic repulsion term. Further, it actually turns out, so I should say this, so it turns out that, let me write this out another way. Let me actually make another remark. And this is a kind of important one because this is a principle that we've played with a lot. So in fact, so here's another point that I should make. So this is, let's call it D. So in fact, the SDED is equivalent to, let me write it out in the following way. So let's write it out as d lambda t is equal to grad s of t. Let me not be too crazy. Let's say d lambda I is equal to grad s lambda I. So this is actually so what this really, another way of thinking of Dyson-Brownian motion is this is really stochastic gradient descent of Boltzmann entropy. Where the Boltzmann entropy over here is log of volume of group orbit. So it turns out that this guy over here, you can write it out as the gradient as the log of the volume of the group orbit. So this is where I'm going with the DLN. So the reason I start out with the DLN is I kind of showed you this group structure. The group is much bigger. It's a product of orthogonal groups. But there's a similar version of that theorem in that setting. And this is the form in which the structure generalizes. So in all of these problems, what's happening is that you have the Riemannian submersion. There's a group orbit upstairs. The volume of the group orbit is or log of volume of the group orbit is an entropy. You can compute the entropy. Its gradient is basically a mean curvature, and you have this structure. Okay? So you can understand the structure in the simplest case in just a circle, but in all of these problems, okay, the calculations get harder and harder. The group, the curvature calculations, thank you. So the group, curvature calculations, et cetera, get more complicated, but the insight is fundamentally the same. I'm a little bit concerned. Yeah. Yeah. So let's go back to that. So what we're trying to do is to build a rigorous theory that'll kind of interpolate between two different observations. One is a rigorous mathematical observation, and the other one is an empirical observation. So the empirical observation is that this balanced manifold is stable, right? Is stable in the numerical sense. You run the numerics, that's what you're ending up with. And that stability seems to be in contradiction to the theorem that you prove. So if you've got exact dynamics, that is not happening. When you do numerical dynamics, that's what's happening. So, okay, I mean, actual numerics is different from what I'm kind of like the insight that I'm projecting down onto it, but I'm saying like, okay, what's one way I could think about the discrepancy between kind of the numerical calculation and the deterministic calculation is I keep thinking that numerics, if I send the discretization error to 0, I know that the numerics will converge to the flow, but actually maybe I should be thinking about that convergence as a deterministic convergence plus small noise. So imagine that we've got this noise over here, but imagine that you're putting in an epsilon in front of this. So what I'm really thinking about is I'm saying, okay, well, maybe we don't like our fundamental model. So let me write it out, actually, because that's where I really want to go with this. So in some sense, what I'm doing is I'm changing my model. So our first model was, let me write it out this way, W dot is equal to minus grad W e W. And what I'm doing is I'm saying, let me replace this with this dynamics. So I've still got my dominant term is still the deterministic gradient descent. But what if I add to this a small noise? And so now I'm going to need some kind of, let's say, a fancy, so where xt is kind of noise in this big space. But now I'm imagining I have small noise. And so where I'm going with this is there are theorems that I can prove for the stochastic gradient dynamics. And what I can do is I can even kind of play around with the noise over here and say that, well, actually, maybe the noise should be different in the null directions, because over parametrization, really, you kind of think about the null directions being different from the other directions. And so I'm introducing an anisotropy parameter over here. And so I can have a little bit of non-trivial noise and I put it all into the null directions. And what I would like to say Okay, we can't prove this, by the way. We're not, there's some issues, and it may be that we have to kind of tweak our model a bit. But what we're trying to do is we're trying to understand the stability of this piece. And now earlier we had our deterministic dynamics over here. Now what I'm doing is I'm adding a jiggle to my deterministic dynamics, but only in the tangent direction. But what that's giving me is a small normal velocity. And I'd like to say that so I'm looking for kind of concepts like entropy solution over here. I'm trying to say that I should think about this dynamical system as the epsilon going to zero limit of this dynamical system. For this dynamical system, I can prove theorems. And for this dynamical system, I can prove theorems that make the curvature come out naturally. So those are the dots I'm trying to join. Okay?
I'm just like, the natural stochastic rate will only be pointing so they won't be pointing
Oh.
It'll be sort of orthogonal to the group action.
I don't know. What are the actual dynamics? You're doing some floating point operation calculation with a numerical scheme on some GPU. Like, what are you actually doing?
Okay. I guess I'm just saying that there seems to be a discrepancy between
Oh, absolutely. Yeah, so you're right. So what I'm trying to do is I'm trying to understand why is the zeros. So I've got theorems that tell me like this fiber is super special. I've got a Riemannian submersion theorem. After that, we were able to say, oh, actually, it's not just a Riemannian submersion theorem. You've actually got a kind of zero mean curvature. So where is curvature coming from in this problem? Where on earth is curvature coming from the numerics? And so I'd like to say that the curvature effect is coming from the noise. Okay, so I mean, by the way, this is noise in a very different sense than, when you really think about SGD, where the noise is really coming from is like you're doing batch processing. I'm not sure if Changzhou is, but you can do, there are kind of theorems that say like associated batch processing, there's a kind of diffusion limit of your algorithm. So I'm cheating a little bit. I'm just saying like, I've got this empirical observation. Can I make a clean, rigorous mathematical theory that will tell me that this is special? And so what could that theory be? Well, one of the ways I'm going to guess that theory is I'm going to look at the theorems that I can prove that are associated with the Riemannian submersion geometry. So the theorems that I can prove are things like I can say that like I can compute group orbits. I can compute their volumes. I look at those computations of volumes, I'm like, oh, that reminds me of random matrix theory. So there's a bunch of stuff, like there's a kind of formula for the volume. That looks like random matrix theory. So then I'm like, okay, how do I relate random matrix theory to curvature? And that's this type of theorem. Okay. So that's where I'm going. We don't have it fully. What we do have is a kind of a restricted result on the balanced cone. And there's a catch. The catch is really that the group action preserves the balanced cone. It does not preserve the other guys. So you end up kind of somehow, there's a separate group action. So you really need to dig into the geometry more and more. There's theorems that you can prove, but it's like the mean curvature calculation for this guy. We still don't have it fully. Computing the tangent space, finding exactly the right parameterization, we don't have it fully. Yeah. So wait, there's a question over there. I'm actually ready to wrap up. I don't think there are other things that I could say, but I think we're kind of at that point in the afternoon where I just like take on questions. Yeah. Sorry, you have to just speak a bit louder.
Is this Boltzmann entropy in your mind supposed to be like related to this low rank?
Not entirely, actually. So by Boltzmann entropy, I really just mean, logarithm of number of states. And for me, number of states over here is volume. So by Boltzmann entropy is for me giving rise to the curvature effect. So it's kind of the gradient of the Boltzmann entropy. So this actually turns out to be a general theorem sitting in the mean curvature in the curvature flow area, in the curvature flow literature. So the gradient of the entropy in each case ends up being the curvature. The relationship to the SE is through stochastic perturbations. The stochastic tangential perturbations are giving rise to the curvature. The low rank effects are actually seem to be much more subtle. And the low rank effects really relate to, it's related to what you're saying. The low rank effects are coming out of the entropy, but it's really related to how you're blowing up as you hit, how the volumetric factors are blowing up as you go towards the low rank matrices. And over there, we don't have as precise an understanding. So it should be related, but the reason I'm a little bit cautious is that I don't understand exactly how to join the dots because I don't understand the kind of stratification of the space. I don't know if that's too much information, but the answer is not really, or yes and no. It's related, but I don't know specifically how it's related. Yeah, Philip?
Somehow maybe I missed it, but it seems
Yeah.
that this observation of Wittenberg et al. That says that it's reminding
Yeah.
never really used.
Oh, no, I'm using it. Okay, so I'm not. I'm not using it just yet, but I am using it in the sense that there's a theorem that follows this theorem, which is, so what I've done is I've changed my model upstairs, and I need to say what happens downstairs. Actually, so that's the perfect question because this is where I will end. That is exactly the right question. So it's slightly more refined than that. So I'll just draw a picture rather than. Okay. So the Westekenberg et al. Observation is that you start out. Okay. Now let me just explain. So you start out with the deterministic dynamics. You start out on the balanced conic, and when you push down, you've got non-trivial gradient dynamics downstairs. So the theorem that I'm going to state over here is start out with this equation, choose the noise over here to be tangent. So we're going to look at a stochastic dynamics on the balanced cone, and the theorem that I'm going to state, or the calculation that comes out of this, is that so consider star epsilon. So this is actually the last statement. With W0 belong to M0. And I'm going to now make it a projection onto tangent space of M0 dxt. So this is Brownian motion in the ambient space. This is the projection onto the tangent space over here. So I'm just doing stochastic fluctuations over there. So then W dot is equal to minus Riemannian gradient downstairs of the entropy plus epsilon S of W. Okay. So that's the theorem. So you get a deterministic dynamics downstairs, and the deterministic dynamics downstairs is gradient flow of a free energy, where now you've got energy plus an entropy. So stochastic dynamics upstairs gives you deterministic dynamics downstairs with an entropic factor. And there's a version of this where you have anisotropic noise too. So it's really like the Dyson-Brownian motion calculation, but you can do it in the DLN context, and you get a kind of gradient descent or stochastic gradient descent of a free energy downstairs.
Where did the stochasticity went?
The stochasticity went out. So what happened is kind of the stochasticity. So that's kind of like the Dyson-Brownian motion inside. So you're putting the noise into the tangential fluctuations, and it kind of gives you a deterministic piece regarding the observable. No, I'm just saying that this is the equation downstairs. It's a deterministic ODE downstairs. That's kind of the point of this kind of putting the noise into the tangent directions. It's like you go back to the example with the circle. Tangential fluctuations, but the radius moves deterministically. Dyson-Brownian motion tangential fluctuations, eigenvalues move deterministically. So over here, put the noise into the tangent directions, you will move downstairs deterministically. But now with the Riemannian gradient.
Do we understand like some complexity properties of heat in geometry?
So over here, I didn't my energy could be whatever I wanted. So this is true for any energy. So, of course, it's convex with respect to the flat metric. But we don't know if it's convex with respect to the Riemannian metric that you're getting downstairs. No. We can prove convergence, but the convergence comes out of a Loyasowicz theorem, not so much a convexity theorem. There is a theorem saying that you converge, but it doesn't come out of convexity. Yeah, we don't know. So we kind of have an empirical observation.
You could check that all of the sound points, all of the different
We don't have, that's not what seems to be, so as I said, the numerics are that you're converging, and you're converging to a low rank matrix. We have a theorem that says you converge to something. We don't have a theorem that says that you converge to a low rank matrix. Like, I'm just saying that this is the primitive knowledge of this problem. I'm not saying that it can't be done. I'm not saying we have, but I'm just saying that this is the stuff that we know. I'm just saying that the problem has a much richer structure than one would kind of get at first sight.
Are you aware if people, because for example, in like
no, there are, so like, yeah, I mean, I'm aware of the work by like people like Strabo, or like, you put in these proxies and you try to do stuff. No, it's just, that's not what you're getting over here. It's just that this does something different. But everything that we have is exact. So the formulas are exact, the metric is exact. The convergence theorem uses Loyasowicz, which is something I'm a little bit wary about. But it's just a different structure. I don't see any real reason to kind of squeeze it into some other structure, actually. This is the structure of the problem. That's all there is to it. Yeah.
From this, not maybe like guess that among all the W's that maybe the W that
I would love to be able to pin down something like that, but we're not there. So this is literally where we are, like, as of the end of last month, or a kind of variant of this where, like, I don't have, I could put in a beta parameter as I did earlier, and I'll get a kind of Dyson type beta stochastic version. So I get a kind of literal kind of Riemannian. So the point is that you get a Riemannian Langevin equation downstairs. I would say the connection with kind of the machine learning literature seems to be like Montanari and Dempala and people like that seem to get Riemannian Langevin equations out of particular algorithms. Over here, we kind of get it out of Riemannian geometry. And so what's that actually, is that really corresponding to a kind of minimizer? Do I really have a theorem that says that the minimizers over here are low rank? No, I don't. That was what you were asking, right? No, we only have numerics. And actually, it's quite subtle. I mean, we did all sorts of stuff, like we played with different depths. We did kind of several rounds of numerics. It seems to be a little bit more subtle. We don't quite get it. Maybe the numerics may be kind of a little bit off because kind of like the rank stuff, the rank stuff doesn't fit so cleanly into what I'm saying over here. And so it's not a place where, like, we're not there. I feel like we're on the right track, but we don't have a result of that nature. I think there was some other question somewhere. Yeah.
I'm just wondering if there's some way I can understand
Oh. Okay, yeah. I can, yeah. So the generic structure is always Riemannian submersion. So what the structure that you need to kind of go from, so the structure that you need is you need to start out with a Riemannian manifold. It has to have a foliation by group action. The group action has to be an isometry. And then everything that I'm saying so somehow works. So you have a space, the space is foliated by these group orbits, so you get an entropy which corresponds to the volume of the group orbits. But the group orbit has to also be an isometry, and then you get an equation downstairs which is like a gradient descent of gradient descent. So your gradient descent of energy downstairs gets modified to gradient descent of free energy. where you have energy plus an entropy, and this entropy is the volume of a group orbit. Yeah, okay, fine. I mean, I'm not in that fan. Yeah, you're right, exactly. I mean, otherwise I don't know how to do the computation of the volumes. Yeah, absolutely. Yeah. I'm still working very much in the realm of examples. There is this theorem that we use, but it's always we're very much in the realm of the examples, and the examples are kind of already kind of a little bit tricky to kind of do the computations. No, we don't use any of those special. Yeah, we just use only geometry and general principles. So that was the weird thing. No use of determinantal formulas. So like there are interesting questions, right? Like so somehow. So with the Dyson-Brownian motion case, we know exactly what the equilibrium configurations are. These are kind of zeros of like the Hermite, the zeros of the Hermite guys. And so in some sense, the new statement that we're making is that you lift it upstairs and you get the associated group orbit. This group orbit is kind of this minimizer of this entropy, and it's got geometric properties. So weird as it seems, considering how much we know about Dyson-Brownian motion, this fact is not out there. In some sense, it just feels like it should be just an interpretation of known facts, like a geometric interpretation of known facts. But it's not, it's not a way of thinking. Like with Dyson-Brownian motion, with RMT, you just kind of work with the algebra of the matrices and you do all the calculations. And so somehow those are the tools that you use. You're not used to using geometric tools. And you use the geometric tools. You don't want to go back and redo that theory from scratch, though I mean, somebody should do this, but like, I don't want to do it. But it's just a amazing geometric fact to me about like, Dyson-Brownian motion. We have got so much mileage out of this example by just playing with it in different spaces in different ways. So this actually came out of like the same Nash embedding stuff. So, yeah. But in some sense, the insight really is kind of like noise in tangent space gives you curvature. Super simple fact, super useful fact. So, yeah. Yeah, oh, absolutely. Thank you very much.